Okay. So today I thought we'd do something a little bit different. We did the Constitution and then we did a little bit of grammar. Today I thought we'd do a little bit of science. So, what I want to do is a beginning electricity course. Nice pen. So, we all have electricity. It's everywhere, right? It's electricity is probably the biggest advancement ever in the history of mankind, because it's allowed things that we could never have done without it. Light bulbs instead of candles, all the electric appliances we have, the computers, the TVs, communication, everything is based on electricity. So the question is, what is electricity? And how does it work? So there's some basics here that I want to explain to you. How electricity works. Okay. Electricity is a flow of energy. It's not something you can see because it's energy. You can only see it, you can see it in the form of a spark. A spark is electricity out in the air. But what it is energy. It's not a thing you can touch, although you touch it, you do know. It's a flow of electricity. So, what is this? Well, all of matter is made up of atoms. And atoms look something like this. Okay?
Toby just pushed your stool.
Toby. Everything that we see looks like this. If you could look at it at the very lowest level. These are called atoms. Okay? Atoms are little pieces of matter. Everything in the world, including the world, is made up of atoms. How this is put together determines what it is, but everything looks like this. There is two parts. On the inside, there is a nucleus, N-U-C-L-E-U-S. And on the outside, there is electrons. In the nucleus, it's made up of two things, protons and neutrons. These words matter because this is the basis of electricity. The nucleus is like a little ball made up of protons and neutrons, and there's different numbers of those, and the different numbers of those makes what it is. Water is one collection of neutrons and protons with electrons. And it's different things. All the elements, well, water is molecules, but we're not going to go there yet. All of the basic elements of nature are based on this. So if you have 3 protons and 3 neutrons, it's one thing. If you have 4 protons and 3 neutrons, it's a different thing. That's what the elements of nature are. But what's happening is these electrons are flowing around in a circle. Just like the solar system has a sun with planets rotating around it, that's what this is on a really small scale. You have the nucleus, which could be like the sun, and you have electrons, which is like planets, floating around it. This is the basic energy of nature. This is just always happening. It never stops. So, these electrons have energy, and they have what we call a charge. The reason it's flowing around is because of the charge. Electrons have a negative charge, and protons have a positive charge. Okay? So what's happening, you can kind of think of this like a magnet. It's sort of the same thing. There's two parts of a magnet, right? And if you put two positive ends together, they push apart. They don't do anything. If you put a positive and negative on a magnet together, they suck together. So opposites attract in nature. When you have a positive and a negative, it attracts. So what's happening here, this nucleus in the middle is positive. Neutrons are neutral. They don't have a charge. No charge. So they don't matter. The proton is pulling the electrons to it. But the electron is in an orbit. So it just keeps floating around. Electricity is the ability to use this energy. What happens is you have some source out here of energy. And you hit this atom, you hit that electron. You know what that electron does? He flies out of orbit and he jumps into this one. The atom sitting next to him. Well, the rule of nature is you always have to have the same number of electrons for any given atom. You can't have too many. So he now has one extra electron. He can't have that. So what he's going to do, he's going to kick it off and go over to here. Well, wait a minute. Now this guy has one too many. He can't have that. So he's going to kick this off and it's going to go over there. You don't know which electron is moving, but what you know is the flow is that if you throw an electron in, this guy goes to there, this guy goes to there, and it flows all the way through forever. Never stops. Because you started a chain reaction by sending an electron in here, and because every atom can only have a certain number of electrons, every one has to throw it off to its neighbor. This is what a wire is. Anything that has the ability to do this is called a conductor. That's what a wire is. So what's happening is, if you take energy and you throw it into something that is a conductor, like a wire, all the way down that wire, instantly, at the speed of light, these electrons are jumping around. So a circuit means an electrical circuit. How do you use this energy? All you have to do is have a source of energy here, like a battery. Battery, remember, has a positive and a negative charge, right? Starting to look familiar? These are all positive and these are all negatives. So if you take a wire, I drew this upside down, but if you take a wire and I connect this wire, let's say this is a wire, okay, made up of all these little atoms. If I take a battery, connect it there, and then on the other end of the wire, connect it there, I now have a circuit. And what's going to happen is the electrons in here are going to start flowing out. They flow across this whole thing, and they come back, and they come into the battery. And it goes forever. As fast as this can generate electrons, it flows to the wire. That's called a circuit. That's what electricity is. It's these electrons flowing through. If I break this wire, what happens?
It doesn't come back in.
It can't come back in, so it can't push any more out. So there's no circuit and electricity stops. You have to have a source of positive and negative in order for electricity to flow. If I take this wire and put a piece of plastic here, what happens? Paper. Something that breaks the flow, that does not act as a conductor, is called an insulator. So it's the same as breaking the wire if I put a piece of plastic there. It stops the flow because the electrons, they come up here and they stop. Okay, well, the guy in the end has one too many. He's stuck. He can't send it anywhere because there's nowhere to take it. An insulator does not accept electrons. A conductor accepts electrons. So a conductor is anything like wire, water, metal, basically anything wet. So that's what's happening down at the lowest level. That's why when you look at the plug in the wall, there's two sides, right? There's two prongs that go in. Why is there two prongs?
A plus and a minus.
Sort of. There is always two sides because you have to have coming out and going back in. If you just have one side, it doesn't work. So why is it you get shocked if you take a knife and stick it into the outlet? Why does it hurt? Where's the circuit? If you have an outlet and there's two sides and you have somebody over here with a knife in their hand and they stick it into one side, that's not a circuit, right? Why would you get shocked?
Metal.
It is, but there's no return to the other side. So here's a very important concept. We are all on the earth. The earth is dirt. What does that tell you?
Goes through the dirt.
Dirt and water is a conductor. Anything with moisture is a conductor. So the thing that you don't know is this guy is on the earth, which is a conductor. So he's connected to the earth. This plug is always connected to the earth. All of this electricity in the plug is trying to get to the earth, just like in the battery. So when you make a connection between either side of this and the earth, you get shocked. Because the electricity flows through you as a conductor because you are a conductor. Because you have water. Remember when we did the experiment the other night? And you could touch somebody's hand and it would make the thing beep? That's because electricity is flowing through you. You are just like a wire. That's why you have to be so careful around electricity. That electricity we were working with was really tiny, so you didn't feel it. But it went through you. Because when you touched hands, it worked, right? This electricity in the wall is not tiny. It's huge. It has enough electricity to kill you. That's why you never touch it. That's why you're really careful around it. So, this is also how electric fences work. Think about it. How is there a circuit in the electric fence? Let's say you have an animal out here. Let's make an animal. I don't know what that is, but it's an animal. And here's an electric fence. You have a charge controller that has two buttons on it, right? Two connections. One goes to the fence. Where's the other one go?
The ground rod.
To the earth, the ground rod. Often abbreviated G and D for ground, because it's shorter. So you do have a circuit. When this guy's nose touches the fence and he's standing on the ground, you now have a complete circuit. That's how it works. That's why in the winter, this works really well. In the summer, when it's very, very dry, the drier this gets, the less it works. In the middle of summer, when it hasn't rained for 3 months, he'll get a very small shock. Electric fences don't work well in the summer because you're depending on his hoofs touching the ground and the ground having enough moisture to connect to this ground rod as a conductor. That's how the electric fence works. If you're in rubber boots, rubber is what? It's an insulator. So if you have a guy here, a farmer, with rubber boots, what's going to happen to him if he touches the fence?
He's not gonna get shot.
Hopefully not. What happens if his boots are covered with mud? What happens?
Well, he has the earth on.
He has the earth on the outside of his boots. He has clothes on. If his clothes are any damp at all, and his clothes touch the mud on his boots, you now have a circuit. Water makes a circuit, so anything with any moisture is a conductor. So if your clothes are perfectly dry, he's safe. If you're sweating, like in the middle of summer, then the sweat that absorbs into your clothes is enough to make a conductor, and you're going to make a circuit from the earth on his boots to him, and it's going to hurt. So anytime you make a circuit, it matters. The reason nothing flows, how do we put an electric fence up? What's on all these wires here?
Electricity.
Yeah, and why doesn't the electricity just leak out? How do we put up an electric fence? What's the first thing you do?
The electrical wire.
No, before the wire, you have to have something to hang the wire on.
A T-post.
And?
What else is there?
One of those plastic things.
Plastic! What is plastic?
Insulator.
So the plastic that's touching the wire and the metal T-post does not let electricity flow through it. Therefore, it's an insulator. So it keeps the electricity in the wire. Otherwise, if you just wrap the wire around the T-post, what would happen?
Shock the T-post.
It would shock the T-post down to the earth and go back. So you see the principles at work here. You've always got to have a complete circuit. Why can birds land on here?
Because they're not on the ground. They're not on the earth.
They're not on the earth. They can sit on a 100,000 volt power line out there and never get shocked. They are full of electricity, but it can't go anywhere. Because electricity is a flow, it only has any effect if it can go somewhere, if it can move. Electricity at rest is a battery. It has the potential to be a flow if you connect across it. Otherwise, it's nothing but a storage spot of electricity. Okay? Another very important concept. Now you know how it works. There's a little bit of a change here you need to understand. Why these are actually more dangerous than a battery. There's two reasons. There is two kinds of electricity. There's DC and there's AC. The difference is DC is direct current. We say current because it's a flow. Direct current or direct flow. AC is alternating current. Any ideas what that might mean? Knowing what you just learned? Direct current is what a battery has. Okay? It means this end is always plus, this end is always minus. The energy always flows across the two in one direction. One direction. Okay? So what would alternating current mean?
Goes back and forth.
Goes back and forth. Both directions. So with alternating current, you have a generator, like we have outside behind your tractor. You have a generator. The generator is making electricity across two wires. Part of the time that's plus and that's minus. time, this is minus and that's plus. It switches back and forth very fast. In America, this switches back and forth 60 times per second, which is a number we call hertz. Something that switches back and forth is at a rate is called hertz. So if you look at the bottom of a device, you'll see 110 volts, 60 hertz. In Europe, it would be 50, because they chose, for whatever reason, to be different. So their standard is 50 times a second. The two are not compatible. Everything built in America is designed for this to happen 60 times a second. Now, why would they want to do that? Doesn't that sound really complex? Why not just have a battery and just go straight all the time? The answer is there was a big debate about this. When this was all discovered, you look at history. Nikolai Tesla, Thomas Edison, the guys that discovered all this stuff, had a big fight between these two. And the bottom line is, this one is certainly easier to deal with because it's always the same. This one is hard to deal with, but it has one huge advantage. Because it's changing back and forth, it works really well for long distances. So if you're going to make electricity in Nevada and ship it to California, that means you have a wire that is miles long. If you had DC, that wire would have to be huge because it has to support all that current all the time. If you do it in AC, the wire can be tiny, relatively speaking, because the energy is going back and forth, back and forth, back and forth. So half the time, there's nothing flowing. If you think about it, back and forth means half the time it's going this way, and the other half the time it's going that way, which means half the time it's not going anywhere. Because it has to stop in order to reverse. Back and forth, back and forth. So what happens is AC is used anytime you need to move electricity a long distance, because it's way more efficient. DC is used anytime you're going to use electricity right there, like from a battery. Two different things. Very different things. It's the same process. The only difference is, with AC, there is no plus and minus. There's only two connections, and that's why we have on the wall. Which side is plus? Doesn't say, right? Because there isn't a plus. Every 60 times every second, it goes back and forth, back and forth, back and forth. So there's no plus and minus here. That means both wires will hurt you. Either side of this plug, if you touch it, either side will shock you just the same. With a battery, it's different. But there's one other important thing besides AC and DC. One other important concept I want to cover is this. Volts and amps. Look on the bottom of anything that uses electricity and you'll see these terms. Okay? Volts is pressure and amps is flow. Electricity works just like water. Okay? If you put water into a pipe, let's say we have a great big thing of water. And we're taking it out the bottom, and we have a little skinny hose. What's going to come out of here is going to be a little bit of water. If we have a great big fire hose, what's going to come out? A whole bunch of water, right? The flow is changed by the size of the hose. The way you measure flow in water is gallons per minute. In electricity, it's amps. So 10 amps equals 10 times as much flow as 1 amp. You measure it in amps. If you look on any device, it'll tell you how many amps or how many watts, which we'll get to in a minute. This is a measure of how much it lets electricity flow, this device. How big is the pipe inside of it that sucks the electricity. For instance, a heater is a lot of amps compared to an electric toothbrush. A heater will take 10 amps, where an electric toothbrush might take half an amp. The amount of flow is how many electrons are doing this all at one time. It's not one, it's a whole bunch. So the flow is a measure of how wide this is. Is there 1 million electrons doing this, or is there 2 going across? That's the flow. Volts is different. Volts is the pressure. And water, it's measured in pounds per square inch. It's how hard it's trying to push. Okay? So it's the same thing. 10 volts is equal 10 times 1 volt. Just like 10 psi is 10 times 1 psi. So think of it this way. You take a water hose, and if I set the well pump at 10 psi, the water's going to barely come out because there's not much pressure to push it. If I increase the pressure at the pump up to 60 psi, now the water's shooting far out, right? Because there's pressure pushing the water. Same thing with electricity. The volts or the pressure is determined by the battery. Let's think about some batteries. What do you have? Most batteries are 1.5 volts, right? Some of the bigger batteries in the car is 12 volts. Anybody know how many volts are in here?
120 or something?
120 volts. What does that tell you? This has 10 times the pressure as that one. So think of it like a little battery. This is actually 100 times smaller. That little battery you hold in the hand, you can touch both ends and it doesn't do anything. You can't feel it. Because there's not enough pressure to push it through your body. Your body is like a little tiny hose that only lets a tiny bit flow through. And there's not much. If you take a wire and put it across both, the wire gets really hot and the battery could explode. Because now there's enough pressure, even at 1.5 volts, to push electricity through. If you move down here and you touch a finger to one of the wires there, it's going to hurt. Because there's 100 times as much pressure. It'll overcome you. Those wires, you know the rule, don't fly kite around wires. You know why? Those wires you see outside are often 10,000 volts, 100,000 volts, even 1,000,000 volts. You see on those, if you look when you're driving around, you see the electrical towers, and they've got this big old long funny looking insulator holding the wire at the end. It can be 3 feet long. Why? Because it takes that much to keep this much electricity in the wire. At some point, there's so much pressure that the electricity jumps out and goes through the air. That's a spark. When you have enough pressure for the electricity to jump out of the conductor and actually move through the air, that's called a spark. So these two things work together. Pressure and flow are volts and amps. And you can, this is the last concept we'll look at, you can actually determine how much electricity something used, because these two together combine into watts. Watts is a measure of power. Okay? Go get that little heater I just bought. Every device, by law, has to say on it how much electricity it uses. So let's look on the back of this and see what it says. Okay, there's always a label. In this case, there's a label right on the bottom. Volunteer, please. What does it say? You're looking for volts, amps, or watts. You see it?
120.
Yeah, VAC. That's volts AC. We know those terms now, right? It says 120 VAC. That's volts of AC power. It doesn't work on a battery. It expects alternating current at 120 volts. What else does it say?
I can't see it when you read.
What else does it say? Let's see if we can decipher this.
Got heating power of 1,000 watts.
Ah, there's a term we know. Watts. Or
1,500.
1,500 watts.
It's got 60 hertz.
We know that one. What does that mean? Don't take it to Europe. It won't work. So here's how you interpret these numbers. There's a really simple math formula that says volts times, I'll use the time symbol, amps equals watts. Okay? So, tiny little math lesson here. This is the formula you can use. What you happen to know, this is 120 volts, 1,000 watts. So we can plug in, it's 120 volts times, I don't know what that is, equals 1,000 watts. I can now figure out how many amps it's going to pull. So to do this, what you do is you divide both sides by the same amount. It's 1,000 on this side, so I'm going to divide this one by 1,000. And I'm going to divide this whole side by 1,000. What's 120 divided by 1,000? I actually did that wrong. I'm going the wrong direction. When you're solving a problem, you want to get rid of everything to leave this guy by itself. Okay? Pay attention. This is important. We're going to have a lesson on this soon. I want to find out what this question mark is, which is amps. So what I'm going to do is I'm going to divide this side by 120. So this is equal to just, I canceled that out. So I take 1,000 divided by 120. What is that? If you take 1,000 and divide it by 120, my question mark is going to equal, if this was 100, it would be 10. So it's just under 10. So let's call it 9. So if it tells you volts and watts, you can figure out how many amps it's going to draw. If it tells you volts and amps, you can figure out how many watts with this same formula.
8.
8. I was 1 off. So that heater, when it's running at 1,000 watts, pulls 8 amps. When you set it on high and it's running at 1,500 watts, it's going to pull more than 8 amps. It's going to be just over 10. So you see, here's the deal. I did all this to say that electricity is the flow of electrons through a conductor. Anything in this list is a conductor, and there's more things that are. You can do an experiment. You can take a battery and a light bulb and anything you want and touch those two together and see if it's an insulator or a conductor. That's the experiment we did the other night. The measure of how hard it pushes is volts. The measure of how much flows is amps. You can have high voltage, low amps, or you can have high amps, low voltage. Both of them measure how much electricity, which is in watts, how much power. Watts is what does work. Volts doesn't do work by itself. You actually have touched over 100,000 volts. You know when? Here's a tricky If you have a dark room and you do that with a balloon, you rub it on your shirt and you hold it up and it makes sparks. You ever do that? Well, you can do that. If you rub a balloon so it sticks to you and then you start to pull it away, you see sparks in a dark room. Those sparks are up around 10,000 volts. The reason it doesn't hurt you is because there's no amps, so there's no power. If you increase one of these without the other, you have no power. All you have is the potential for power. On the other hand, if you only had 1 volt, but you had a large flow, that would be, you couldn't touch it. It would kill you. So, low volts, high amps will hurt you because it's high watts. High volts, low amps will hurt you unless they're low enough so it can't go through. So watts is a measure of how much power electricity has. So if you're looking at a heater, and you see a heater that says 1,000 watts or 1,500 watts, you see another heater that says 10,000 watts. What do you know? The 10,000 watts is going to make 10 times as much heat and cost 10 times as much to run because you're using 10 times more electricity to generate heat. You're doing 10 times as much work at 10,000 watts as 1,000 watts. So this little 1.5 volt battery doesn't hurt you because 1.5 volts at the amperage that it can create doesn't hurt you. You can take a 9 volt battery. You know one of those funny looking 9 volt batteries?
Mm-hmm.
And you touch your tongue across those two and it'll tingle. That's what it feels like to have 9 volts flow through your tongue. It won't hurt you, but it'll tingle. It doesn't hurt you because 9 volts at the amperage that little battery can create isn't gonna hurt you, but you will feel it in your body. So that's a quick overall picture of how electricity works. Any questions? Okay, I'm going to stop the tape.